Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In the previous week, you have learnt about RNN, their structure and working. In today's session, we will discuss about long short-term memory, which we call as LSTM structures. So the content for today's session goes like Introduction to Long Short-Term Memory, difference between RNNs and LSTMs, LSTM architecture, gates in LSTM architecture, applications of LSTM, bidirectional LSTM and stacked LSTM. We will start with the introduction to long short-term memory, which we call as LSTM. Let us take as an example this sentence. My grandparents live in Germany and I visit them every summer, which is why I understand German quite well. So the connection between the location, which is Germany, and the language German is separated by many words. So this is called as long-term dependency in a sentence. Long-term dependency in a sequential data is very important to be maintained to have a meaningful sentence. Now recurrent neural networks or RNNs cannot capture this long-term dependency in sequential data due to vanishing gradient problem. So there is a limitation of RNNs, that is the gradients start becoming very small when it tries to capture the long-term dependency. So that is where long short-term memory or LSTM structure comes into play, and it was introduced in 1997 by Rochreiter and his group in the paper Long Short-Term Memory in Neural Computation Journal. Now we will look into what is the difference between RNN and LSTM. Now RNNs are designed to handle sequential data by maintaining a hidden state that captures information from previous time steps. But they can't handle long-term dependencies. They have one hidden state which captures information from the previous time step. Now we will see how this RNN and LSTM they differ. So we have RNN and LSTM here, and both we are giving input to both of them, and in RNN we have a working memory which is your hidden state, same is there in LSTM as well. Together with that one there is a long-term memory cell also which is present in LSTM, and then we get the output from both the RNNs and LSTMs. We will try to see here how this long-term memory cell helps in mitigating the vanishing gradient problem and helps in getting the long-term sequence in a sentence, okay? Long-term dependency in a sentence. LSTMs introduce a memory cell that holds information over extended period. This addresses the challenge of learning long-term dependencies. Now we will keep on using this term states. In case of RNNs and LSTMs, we will just have a look into what are states in an LSTM. Okay? States are the internal memories that carry information across time steps. Okay? Now here there are two states in LSTM, as I told. One is the hidden state, which we represent by HT. It is a short-term memory and it is used for predictions and passed to the next time step. So it have information of the previous time step and then it is passed to the next time step, and this was already present in vanilla RNN. Whereas in LSTM the additional state that is there present is called as the cell state or CT. So it is a long-term memory and CT carries information across many time steps, which helps in having the memory for a long time, and thus helps in getting the long-term dependencies in a sentence. Now we will have a look into the LSTM architecture. LSTM architecture, they have three gates. One is the input gate that controls what information is added to the memory cell, forget gate that determines what information is removed from the memory cell, what information should be forgot, and the output gate which controls what information is output from the memory cell. Okay. So these are the three main gates in an LSTM architecture. Now just take an example of this sentence allowed students may attend and participate today. Now, if you see the first word allowed is having an effect on attend and participate. So, the first instance or the first input allowed is affecting your fourth and sixth word, okay, in the sentence. So, first instance of the time input influences only the fourth and the sixth output. Now, we will see how these gates are present inside the layers like input layer, hidden layer, output layer, where exactly the gates are present and how they are working. So, we have time steps 1, 2, 3, 4, 5, 6, 7. These 7 I have taken because allowed students may attend and participate today. There are 7 words in that sentence. I have taken 7 instances, time instances, where each and every time instance will take each and every word. Then we have the input layer, these are the input layer neurons. Then we have the hidden layers and the output layer. Okay. Now, we expect the input layer, whatever comes to the input layer, they will go to the hidden layer, correct. Now, what happens is my first input or the first time instance input, which is 1, the word is here is allowed, that is the only word which is affecting my fourth and the sixth word in the output. Okay. So, what happens is we will make the information only for the first time instant to flow to the hidden layer. Okay. So, that is the reason your only this time instant is going to the hidden layer, and what about the other things? This means that the gate is closed. Okay. Here also gate is closed everywhere other than the first instance. I am not allowing any information to flow from my input layer to the hidden layer. Okay. So, this is my input gate that is present just before the hidden layer. Then what happens? In the hidden layer, the information will be passed. So, we are passing the information from the first, second, third instances like this. Why we are passing these all the information here? Because my information, the information from the first time instance is having an effect on the fourth instance output. So, 1, 2, 3, 4, probably this is the output where it will affect, and again the sixth output it will affect. Okay. So, till this point we will allow the information to flow, and after the sixth word, which is participate, there is not much of important, this allowed does not have any effect on the word today. So, that is the reason this gate is closed. Okay. So, these are called the forget gates. It is forgetting after till whatever time is required it is keeping, and then it is removing. Now, we expect from the hidden layer it will go to the output layers. Okay. And what happens here? After the output layer, we expect the predicted values from the output layer, which is y1 hat, y2 hat, y3 hat, y4 hat, y5 hat, y6 hat and y7 hat. So, these are the predicted terms or predicted words in my output sentence. Okay. So, what happens here is, you see our fourth output, which is attend, and the sixth output, which is participate, they need the information allowed. Okay. So, what we will do here is we will close all the gates other than the fourth and the sixth gate. That means the information should go only for the fourth neuron and the sixth one. Okay. Fourth instance and the sixth instance. So, this is how this gate also is closed, and these are called as the output gates. So, output gate basically it determines or it regulates how much information should go to the output layer. So, like this, if I want to predict, say allowed students may attend, and you have to predict the next word. So, for that one, this kind of gating structure is used, where the input information is gated or controlled by the input gate, and then the forget gate keeps only the important informations, passes through the time instances, and the forget gate removes it from the time instances when it is not required, and then you have the output gates where exactly whichever time instance required the previous information that flows through, the others are closed. Okay. So, this is how the gates in the LSTM architecture works. Now, we will have a look into the LSTM architecture more in details. So, we have here a 3 node LSTM structure. So, this is my T minus 1 node, this is T minus 1th instance, this is Tth instance, and this is T plus 1 instance. So, LSTM chain with 3 nodes. Now, we will see what happens in these 3 nodes, how the information is passing sequentially. So, from T minus 1th instance, we get 2 things. One is the Ct minus 1 and Ht minus 1. This is the cell state at the T minus 1th instance, and this is the hidden state at the T minus 1th instance. So, these two comes out from my T minus 1th instance, and what happens? Ct minus 1 is the cell state from the previous time step, which is the long term memory that carries information through the sequence. Okay. Ht1 T minus 1 is the hidden state from the previous time step, and it is the short term memory. Now, we will see what happens after this. In this Tth step, we will look what is the structure of the LSTM here. So, we have the forget gate, we have the input gate, and we have the output gate here inside the structure. Okay. Similar things are here also, they are also present here and here, but for explanation we will just look into the Tth time instance. Now, here what happens is this Ht minus 1 goes together with that one. This is my input from time instance T. Okay, this is the input vector that also enters my the forget gate. Okay, so it will go to the forget gate. Xt is the current input vector at time step T. Now, what happens after this one? Ht and Ht1 and Xt, they both go to the forget gate, and what is the output that I am getting from here? Ct and Ht, okay, which is the cell state value at the Tth time step and the hidden state value at the Tth time step. These two goes as the input to the T plus 1th time instance. Now, gates are constructed in such a way that they can be closed or opened at any instance of time, which makes them flexible. So, depending on the requirement, the gates can close and open at any instance of time. So, these gates are flexible gates, and gates are also neural network with learnable functions in them. Okay. So, these are all internal neural networks. Now, we will have a look into how the forget gate is working, how the input gate is working, and how the output gate is working. So, we will look into the forget gate. Suppose this is my forget gate structure. So, the input to the forget gate is the hidden state from T minus 1th time instance and the input vector from the current time instance Xt. Okay. Both of them go inside, and then these two are going through a sigmoid activation function, sigmoid function. Now, what exactly the sigmoid function does? It gives a value between 0 and 1. So, after these Ht minus 1 and Xt goes to the sigmoid activation function, we get output as Ft. Now, what is this Ft? Ft is the sigmoid function working on Ht minus 1 and Xt. So, it is weighted sum of the Ht minus 1, that is the hidden state, and the input at the current state, plus this is a bias term, and this entire thing is going through a sigmoid activation. Okay. What is WF? WF is a weight matrix associated with the forget gate. Okay. So, this is Ht minus 1 Xt is the concatenation between the two vectors coming from Ht minus 1 and Xt, and then they are weighted with the weight matrix for the forget gate, plus the bias term is added, and the entire thing is passed through the sigmoid function. So, The value of ft, as I was telling, the sigmoid activation function's main work is to take it between 0 and 1. So, it gives a value between 0 and 1. So, ft lies between 0 and 1. 0 means it is completely forgetting and 1 means it is completely remembering. So, in between values means it is partially forgetting and partially remembering. Okay. Now, after this one, this Ct minus 1 also comes inside the forget gate. Now, this Ct minus 1 have a element wise multiplication with ft. So, what we are getting? Ft element wise multiplication with Ct minus 1. What exactly is happening here? This ft value is between 0 and 1, we have told that one. Now, when it is multiplied with Ct minus 1 element wise, then some portion of the memory cell, whatever information was there in Ct minus 1, those are getting, or irrelevant information are getting removed from the memory cell. Okay. So, we get ft into Ct minus 1. Now, so this was the architecture of your forget gate. Now, we will look into the architecture of input gate. What exactly is there in the input gate? Suppose this is a black box of the input gate. We will see what are the inputs to the input gate. Once again, ht minus 1 and xt, these are the two inputs to the input gate, and then both these two are going through the sigmoid function and we get it from there. Now, what is this it? Once again, it is ht minus 1 xt is the weighted sum of the inputs from xt and ht minus 1. The weights associated with wi are the weights associated with the input gate. This is the bias associated with the input gate, and the entire thing is passed through a sigmoid function. Okay. So, wi is the weight matrix associated with the input gate, and then we see this ht minus 1 and xt once again goes through a tan h activation function. So, whatever output we are getting here, we are naming it as Ct hat. Now, what is this Ct hat? Ct hat is ht minus 1 xt's concatenation and then multiplied with the weight matrix Wc and added with the bias term Bc, and then it is passed through tan h. Now, tan h always squashes the values between -1 to +1. So, it brings the values in a manageable range. Okay. So, Ct hat, the value of Ct hat lies between -1 to +1. Okay. Wc is the weight matrix associated with the candidate cell, and what exactly is this is a new term, candidate cell. What exactly is the candidate cell? Candidate cell is the new information that could be added to the cell state at the current time step. So, suppose I want to add some new information in the current time step t. So, that can be added using the candidate cell. Okay, and the Ct hat is nothing but the candidate cell. Now, this one Ct hat is getting multiplied with it, and it is element wise multiplication. So, we get it into Ct hat and then it is concatenated with, or there is an additive term here with something which is coming from the forget gate. If you remember, this was our forget gate, and from forget gate we were getting as output ft into Ct minus 1. Element wise multiplication between ft and Ct minus 1, that goes from the forget gate and gets added in the input gates operation, and what we get as the output from here is Ct equal to ft multiplied with Ct minus 1, this is coming from here, plus this is it multiplied by Ct hat. So, what we are doing? We are taking information from the forget gate, whatever information was remaining, that we have taken from forget gate here, and we are adding something new which can be adding something new that may come from the tth time step. Okay. So, this Ct is basically the cell state update, and Ct is the main memory of the element at Ct is the main memory of the LSTM at time step t. Now we will look into the architecture of the output gate. What exactly is present in the output gate? So once again, let us have this one as the output gate, and the inputs here is ht minus 1, xt, ht 1 minus 1 as I have told is the hidden state information from the t minus 1 is time instance, xt is in the input at the tth instance of time, it is going through the sigmoid activation function, and then what we are getting here is OT, and OT is given by this equation once again sigmoid of WO into ht minus 1 xt plus BO. BO is the bias associated with the output gate, and WO is the weight matrix associated with the output gate. Okay. Then so this is the output gate, and this is what was this, that was this one, this is the input gate. So we have seen the input gate looks like this, and the output of the input gate, as I was discussing in my previous slide, is Ct equal to Ft into Ct minus 1 plus It into Ct hat. Now what happens is this goes and a portion this goes and it comes here and goes through a tanh activation function operated by a tanh activation function. So what is happening is here that whatever is coming out of the tanh activation function, this gets multiplied with the OT. Now what is this what is happening in the tanh activation function, we will have a look, and whatever output we are getting, that is the HT. So HT is nothing but OT element wise multiplication tan H of Ct, because Ct was coming from here, it is going through tan H. So your tan H Ct gives you this term, and then it is element wise multiplication with OT which gives you HT. So HT is the hidden state from the time instant t, and Ct is your cell state information from the time instant t. Okay. And this is the structure of the output gate. So we can see how the output gate is connected with the input gate, and how it is taking Ct from the input gate and then it passing through the tan H activation function, multiplying it element wise to the output output OT, and then giving the hidden states value. So once again the tan H brings the values between -1 to +1, which is a manageable range, and then this OT is basically once again, as it is going through a sigmoid activation function, its value is between -0 to 1. So here also whatever is required, that is kept, and some portions of this is left out or removed. So this is my HT after the multiplication. Okay. So that is the architecture of the output gate. Now we will have a look into how vanishing gradient problem of RNN is mitigated in LSTM. Okay. So cell state update in LSTM is given by, we have seen this one, Ct equal to Ft element wise multiplication with Ct minus 1 plus It element wise multiplication with Ct hat, which Ct hat is the candidate cell information. And then you see this Ft, we have seen in the previous slides also, Ft can vary between 0 to 1. Now because Ft is coming out of the sigmoid activation function. Now when Ft is equal to almost equal to 1, we have this entire thing. Okay, so this is fine. So some value will be there. It is approximately Ct plus 1 plus whatever term is here, It into Ct hat. So there is no problem in the gradient flow in the backward direction. But when Ft equal to 0 or almost near to 0, then this term becomes very low, or almost to, this becomes almost equal to 0. So this creates a problem in gradient flow. But here what happens is, in Ct, together with this multiplicative term, there is an additive term which is It into Ct hat. So due to the presence of this additive term, this Ct never goes to 0 completely, or it does not vanishes fully, and that is the reason the gradient does not vanish. So this is the way the vanishing gradient problem of RNN is solved in LSTMs. Okay. Now we will look into another very interesting concept which is called as the bidirectional LSTM. So, bidirectional LSTM, from the name itself we can see that it goes in both the directions. Okay. Now, why we require this one, what is the architecture, we will see. First, let us take this example. I can book a flight. I want to see what is the parts of speech of this term book. This book can be a normal reading book as well as it can be booking a flight. Okay. Both things can be there. Now, if I scan the sequential data from left to right, I see I can book a flight. So, this can tells it can be a verb, but there is no confirmation. Okay. So, if I look from only from left to right, I do not get the full information about the term book. So, instead of looking only from left to right, we will see we will scan from left to right as well as from right to left. Okay. And that is exactly what is done in bidirectional LSTM. Okay. So, bidirectional LSTM or bi-LSTMs is a type of recurrent neural network that processes sequential data in both forward and backward directions. So, it will once process it in the forward direction, again it will process it in the reverse direction, and then it will combine the results of both forward and backward directions, and then it will give the output. Okay. This allows the model to capture both past and future context of the input sequence. Okay. We are getting from the whatever information is there from the past, that also we are seeing, and whatever information is there in the future, that also we are seeing before doing any prediction. Now, we will see how the bidirectional LSTM structure is looking. So, we have the inputs at various time instances, x at t minus 1, x at t, and x t plus 1. Okay. And this is the input layer, and then we have LSTMs, okay, at x t minus 1 instance, that is tth instance, and this is t plus 1th instance of time. This is now the information we will pass in the forward direction. So, it will flow from left to right. Okay. And here it computes, what it computes? It computes the ht and ct. Okay. In every time step it computes the cell state and the hidden state values based on the previous time steps. Okay. So, it computes the forward direction ht and ct. So, here it will give h t minus 1 ct minus 1, here it will be ht ct, and here it will be h t plus 1 ct plus 1. Okay. Now, we have another set of LSTMs, and the input x t minus 1 goes here separately, x t also goes separately to that other LSTM, and x t plus 1 also goes to the other LSTM. Okay. So, this is now the information will pass in the backward direction. Okay. And here also, here what will happen is in each and every cell ht and ct will be computed. So, here in this case it will be all throughout in all the steps it will be computed in the backward direction. So, this arrow shows in the backward direction what it is computing. It is computing the hidden state and the cell state. Now, we have whatever information we are getting from here, from the forward pass or the LSTMs that are used for the forward pass, they are going here, and whatever information we are getting from the backward pass, they are independently kept, and here they are going, they are taken separately, and there is a additive function or concatenation that is happening. Now, here the hidden states from both LSTMs are layers are combined at each time step. So, your HT is a combination of HT from the forward step and HT at the from the backward step. This should go down. Okay. Okay. So, this is a combination of both the hidden terms or hidden state values from the forward pass and the backward pass. Okay. And this is happening in all the places, all the time instances, and then we get the output at t minus 1 instance. This is at the tth instance, and this is t plus 1th instance of time. Okay. So, this is how the past as well as future information is taken into account when using bidirectional LSTMs. Okay. Now, we will have a look into what is stacked LSTM. Now, stacked LSTM, which is also called deep LSTM, multiple LSTM layers are placed one on the top of the other. Now, why do we want these things? Okay. Suppose I have an example. I grew up in France and I speak French. Okay. So, the layer 1 learns the grammar, the word dependencies and other things. Layer 2 learns a semantic relationship between France and French. So, it is basically learning the hierarchical relationships in a hierarchical way. Okay. So, that is what is done in layer 1 and layer 2. A single layer LSTM may fail to capture complex hierarchical features. That is the reason we use stacked LSTM. So, we will have a look into how this stacked LSTM looks like. So, these are LSTM blocks. This is the layer 1, and if you see, these are the inputs at time instant t minus 1, time instant t and time instance t plus 1. The inputs are xt minus 1, xt and xt plus 1, and then they are flowing from xt minus 1 xt to xt plus 1, and these are the hidden states. This one, the superscript 1 shows that it is from layer 1. So, this is the hidden state from t minus 1th state, and we have the cell state from the hidden the layer 1 t minus 1th time instance, and then here it is h1t, that means for the first layer hidden state at time instance t, and here first layer's cell state at time instance t. Similarly, h1t plus 1 and c1t plus 1. So, these are flowing in a sequential way, and then what happens is we take the output of this LSTM of layer 1 as the input to the other LSTM in the next layer. So, h1t minus 1 goes as as the input to the LSTM in the second layer. Okay. Similar things happen for the other time instances as well, and this is output of lower LSTM goes as the input to the higher LSTMs, and then this may continue. I have shown only layer 1 and layer 2. Okay. So, here this h2 gives it is for layer 2 t minus 1th time instances hidden state, and c2 t minus 1 means the second layer's cell state value at the t minus 1th time step, and then h2t means second layer's hidden state values at the tth time step, second layer's cell state value at the tth time step, and here at the t plus 1th time step hidden state value at the second layer, and this is the cell state value at the second layer in the t plus 1th time step. So, this is the complete layer 2. So, there can be multiple layers up like this, like layer 3, layer 4, and we get the output from here. Okay. So, this type of stacked LSTMs, they are used for where there is complex hierarchical features are there to get those, to capture those complex hierarchical features, these stacked LSTMs are used. And these kind of LSTMs are majorly used in sequential data processing, sequential data where long term dependency is a major concern. We need the model to capture the long term dependencies, and there is a lot of information between there is a lot of words in between two words which are having a relationship between them. Okay. So, those are the applications of, that is where we use the LSTMs. So, okay, I forgot to tell, the stacked LSTM, each layer has independent weights and no weight sharing across the layers. So, every layer is independent of each other, only the hidden state inputs are going to the next layer's inputs. Okay. So, that is how the stacked LSTM works. So, with this one I come to the end of today's session. We will quickly have a summary of what we have done. We have seen, we have started with LSTM structures, and we have started with LSTM structures are used to mitigate the vanishing gradient problem in RNNs, and because RNNs were not able to capture the long term dependencies in sentences because of vanishing gradient problem, which is mitigated in the LSTMs. And we have seen how LSTMs in the different instances of time, how the gates are there as the input gate, the forget gate and the output gate, they are there, and how each time these gates are opening and closing depending on what is the information that is required for which instance output. Okay. So, that is that we have seen, and then we have seen what is the structure of the input gate, the forget gate, input gate and the output gate in an LSTM architecture, how a portion of the information is forgot and how information is passed through the time instances, various time instances. Okay, that we have seen. Then we have looked into what is bidirectional LSTMs. Bidirectional LSTMs are used for capturing both the past as well as the future, and future of a sentence, because sometimes looking into the future is required to have a meaningful information about a word in between the past and the future. So, these bidirectional LSTMs, we have seen that the information passes once in the forward direction, once in the backward direction, and then these are all independently stored, and then the hidden states are combined together to get the predicted output. Then we have seen what are stacked LSTMs and where exactly they are used. So, stacked LSTMs, they are used wherever there are hierarchical features to be captured. So, the stacked LSTM means the LSTMs are stacked in layers. So, there can be multiple layers, one for layer 1, layer 2, layer 3, it can go till layer n. So, they are called deep LSTMs, and where the input from the layer 1 goes, the hidden state output of layer 1 goes as the input to the second layer's LSTM, and finally after multiple layers we get the output. So, that is about stacked LSTMs, and with this one we have covered the LSTM architecture, and I hope you all have found this session informative, and in the next session we will talk about the gated recurring unit, recurrent unit, which is called as the GRUs. We call we will discuss about GRUs in the next session. Till that time, keep learning. Thank you all.